So we showed some Boolean operations you can do on two variables, and from those three operations that we have, we can come up with few fundamental identities that we will use in Boolean algebra. Some of them are sort of straightforward, make sense. Some of them less so. A lot of them are very closely related to arithmetics that you know already from regular arithmetics, which makes it fairly easy to remember them. Nevertheless, we do have to formalize them, because later when we come to work with more complex expressions, they will come in very handy. So we'll go through them one by one. The first identity is called the identity, and it states that anything or 0 will stay that anything. It makes sense. If x was a 0, 0, 0 will stay a 0. If x was a 1, we will get a 1 at the output. Also, anything ended with 1 will give you that something back. Again, you can look at the truth table right here, and you can see that any time that we have a 1 for the y, you will get what x was as the function. These things sort of make sense, but that's the identity. The null identity states that anything or 1 will give you a 1. And this is something we said before. It's a property of the OR gate. As long as at least there's 1, 1 in OR, the result will be a 1. And it's sort of dual. Anything ended with a 0 will produce a 0 at the output, which is quite apparent from the AND gate. As long as we have at least 1, 0, anything ended with 0 will give you a 0. You really need 2 1s in order to produce a 1 at the output. Idempotence tells us that anything ORed with itself will just be itself. 0 or 0 will give us a 0, which is this line here. 1 or 1 will give us a 1. And it's true also for the AND operation. Anything ended with itself will just give us itself back. Now, these are things that you might be asking yourself, why is it important to know? Because when we will manipulate more complex expressions, you will start getting repeating terms in your expressions, and then you can just omit one of them because it will not change the final result. Complementarity. Yep. It means anything or its complement or an inverse will give you 1. And it makes sense because if x was a 0, its complement will be a 1, and anything ORed with a 1 is a 1. And if x was 1 to begin with, then the result will be a 1 anyway. On the same token, anything ended with its complement will be a 0. Because one of them, either x or not x, will have to be a 0. And then, as we saw before, anything ended with a 0 will result in 0. So this comes pretty often when you have a variable ended with its complement, and you can just cross the whole thing out because you get a 0. Involution, I sort of showed it before, and it makes sense. Anything that's complemented twice will just return to be itself. So you take x, you complement once, you get its complement. You complement it again, you get your original value. Because you really only have 2 values, 0 and 1, to go through. Does everything make sense so far? All right. Now using those identities, we can come up with few properties of Boolean algebra. And these properties are very similar to regular arithmetic. It's things like commutativity. Things are computative, yes. You know what I mean. You can read it. Hey? That's the one? I don't know who came up with these. What it means is it doesn't matter the order of the operation or of the variables when you end them and when you order them together. You can either have x or y or x, and you'll get the same result. Which you're thinking it's pretty obvious because this is how it is in math, but it's not always true for all areas of mathematics. So again, we had to formalize it. But it's true also for the AND operation. Anything x and y will give you the same result as y and x. It doesn't matter what order you put them through. Associativity. It tells you that with an OR operation, it doesn't matter as long as you have only OR operations. It doesn't matter whether you do the y or z first and then OR it with x, or if you do the x or y first and then OR it with a z, or the x or z first and then OR it with a y. It doesn't matter. Similarly, you can have x and y first and then end it with z, or you can do the y and z first and then end it with x. Is that what I said? Y and z first and then end it with x, or x and y first and end up with the z. Again, what it means, it doesn't matter if you have a chain of few ends together, it doesn't matter which two you end first. Distributivity, that's actually a nice one. So this is what we think about in mathematics, multiply out. So x ended with y or z will give you the very same result as if you do x and y or x and z. Easy to remember. Now, it's dual, so the equivalent of x or yz will in fact give us x or y, x or z, which is not something you see in regular arithmetic. And this is what we call add out. Now the easy way, it's not so intuitive, this one, but it does come in very handy. So if you can remember the multiply out, and then you see something like this, the way to remember it really well is to think about multiply out, but just change the symbols between the or and the and. And then you have add out. Someone kept saying Demorgan before. There is a guy called Demorgan, and he came up with this theorem. His theorem states that the complement in x or y is the same as the complement of x ended with the complement of y. And vice versa. If we had x and y complemented, it will be the same as x or y, not x or not y. We will talk about the Demorgans theorem a bit more later. But before I do, what I want to show you is this concept of duality. When I was talking about the properties and the identities, I kept saying, here's a property, here it's dual. Formally, a dual of an algebraic expression is to take the expression and change everywhere that you have a 0 with a 1. So if you have constants, 0, you change it with a 1 and vice versa. You take all the operations that are an OR, you change with an AND, and vice versa. You leave any of the variables in place as they are. You leave any inversions as they are. And you get a new expression. Now, there's a theorem that says that if you can prove a theorem about some Boolean theorem, and you take its dual, taking its dual meaning doing those two things, the dual will also be true. So if you can prove 1, its dual will also be true. You don't actually have to prove it. Now, duality is not actually a way to manipulate expressions. When you replace zeros and ones and ors and ends, you actually change the expression. But it's rather a theorem about theorems, that if you can prove one expression, then taking its dual will give you, it will be true as well. And in a sense, what I've done here, I took one theorem, although I didn't prove it, I will in a second. And I said, I'll take all the OR signs and the AND signs and replace them. So instead of OR here, I have an AND. Instead of AND here, I have an OR. And if I can prove this one, this will be true as well by the theorem of duality. Any questions before we continue? Now, those identities that I showed you before, there was an identity, anything or 1 will be 1, for example. Any one of those variables can actually be replaced with the whole expression, which is still true. For example, so this is identity that I showed you before. And now I'll set, instead of x, I'll call it, what do I have in my example? A and B or C. Then I can take this expression and then set it in the equation over there, and then I'll have A, B, or C, or 1. So set this here. And this will still be true. It will still be 1. Now in this case it's true because 1 ORed with, no matter what the result of this expression was, will give us a 1. So it is true here. But in general, you can replace any of the variables that I showed in the identities before, replace them with the larger expression, and they will still be true. And this is a property that will come in very handy. I will show you examples of it in just a second. And you will use it a lot in tutorial and other places when you'll use Boolean algebra, such as the exam. Now, what we've covered so far was identities and properties of Boolean algebra. Let's talk about some useful theorems that you can use to simplify your expressions. There's absorption. And we'll try to prove those theorems. Can anyone see why this is true?
Factor x out, you get 1 over y, and 1 over y is 1.
Well, yeah, that's one way of proving it. I can factorize this to be x1 or y. And then 1 or with anything is a 1. X ended with 1 will be x. And I will get this theorem to be true. Now with this theorem and everything I will show you in the next few slides, it's a good idea to either remember them or know where to find them, because they will help you simplify a lot of the expressions. If you see something like this, hopefully after some experience you'll immediately be able to see, all right, I've got this variable, it's repeating later, but that means that the second term is redundant. I'll cross it out. And obviously I just crossed the term from my expression. I made it simpler. Its dual is also true. Which, first of all, it's proven just because I proved the first one, and the second one is just its dual. I could go on and prove the this as well if I factor it out. We said if we have a repeating variable ended together, this can just be x or xy, which takes us back to what we just proved at the top, and we end up with x again. Questions so far? Minimization, a theorem that says xy or x not y will give me x. Fairly easy to prove as well if you factorize out x. A variable ORed with its complement, one of them has to be a 1 then, and then 1 OR with anything will give us a 1, so this whole thing becomes a 1. X and 1 stays x. And by duality I can give you its dual version, which you can expand out and prove as well. Or you can say, oh yeah, by the theorem of duality, it is true. Simplification, x or not xy will equal x or y. How do I prove this one? Yeah?
X, when we take the add and put them in brackets outside, I know what you call it, but x plus not x in brackets, sorry, x or not x in brackets, and then x or y in brackets.
How do you come?
It's like x or y and z.
Okay, so you edit it out. Yeah. So this is what I said. I missed this for a second as well. Editing out. And then we can simplify it that this will become a 1. Then 1 ended with anything else. And this will just become the x and y here. I would actually prove it otherwise. This is truly correct. Another way to prove it is to actually add a term. I use capitals. I'm adding this one in, which is I'm not changing the expression because this is just a 1. And then I continue this into this. Now those two, which is slightly longer when you think about it, will become y x, or let's just delete this, not x. This becomes a 1, and I end up with the result there. By the way, the dual of this one will give us x and not x or y will equal xy. And this is, well, it's true by its dual, but it's also true if you just expand this out. X or not x will be zeroed out, and you end up with x and y. Then we have a very fun one, not so obvious. If we have something like x and y, not xz or yz, we can actually get rid of the last term and get the identity xy or not xz. I will prove it in the next slide in a second. Just for completion, its complement, oh sorry, its dual, it's not the same as its complement. Now let's prove the consensus theorem. The reason why it's got its own slide, because it's slightly longer. So we start with xy, not xz, yz. By the way, what you'll find, and I think we saw an example of it just before, there's more than one way to manipulate Boolean expressions. And it will become very evident in your tutorial questions for next week that sometimes you just have to see things. You stare at an expression and you need to simplify it. And you're not quite sure how to move on. Usually you might get questions to prove this side, the left-hand side, equal to the right-hand side. Sometimes it's not so obvious how those things go. So first of all, as we saw, there's sometimes more than one way of proving things. Sometimes it's not always so straightforward. And in next week, we'll actually learn some methods how to, in a way, automate this process a bit more. So you don't have to sort of stare at equations until some idea comes out. Nevertheless, we'll start off with hand manipulation of algebraic of Boolean expressions. So what I will do, I'll take this, remember what I'm trying to prove is that I'm omitting that last term is redundant. I will start off by rewriting this by adding in and 1, so I'm not changing anything. Then I can change this 1 into x or not x. We had an identity before, and x or not x will always be a 1, so I'm sort of making this 1 just to be this, and then naturally I will open the brackets. Now another thing that you realize, when I write Boolean expressions, I usually try to order my variables in the same order of the alphabet. So I could have written this as yzx. I usually try just to keep them in order. it's my convention. You don't have to follow it, but I think it makes the work a bit neater. And it will make you sort of see things, different groupings that you will see in a second. Now let's just reorder some of our terms. And this starts to look a bit simpler. What I've done, by the way, I moved this one here and I moved this one here. I just reordered them. There's no problem doing this. I did not add anything else. But now I can see something here of the form that I had before, x plus xy, where xy is sort of my x, and the y up there corresponds to the z. I said I can replace any variables in those identities and properties by a whole expression. So now this can become xy. I'm just running it out. I could have just skipped the stage. I'm running it out. And a similar thing here, xz 1 or xz 1 or y. I have 1 or something, and I have 1 or something. These two just become 1. And I end up with xy or with xz. Which I think about 15 minutes ago, that's what I wanted to prove. So these are the first two terms. I got rid of the third one. If you can memorize this theorem, that's pretty good, because it is a pattern that does come up. If you can see it straight away that you can omit that third term, it will come in useful. If you can't see it, you can always sort of work it out as you go along while you manipulate your expressions. So that's one way of proving things, by starting on the left-hand side, doing all these Boolean algebra manipulations. There's another way of proving things, what we called proof by perfect induction. Proof by perfect induction says, and this is true for any Boolean theorem or for any identity you're trying to prove, if you can prove that the result you get for all the possible combinations on one side is the same result that you will get for all the possible combinations of the other side, that means the left-hand side and the right-hand side will be equal to each other. And this is how I'll prove Demorgans Theorem, by perfect induction. I'll take, if you remember, Demorgans Theorem stated that x or y inverted is the same as not x and with not y. I will try to develop my left-hand side here, develop my right-hand side here, and if I end up with the same result for all the different combinations, that means that it's true. I'll do it on a step-by-step. First of all, calculate x or y, which is just a simple, so simple I got it wrong. Just a simple OR operation. And then I'll invert it. So this will be my left-hand side. So the inversion of this will give me this. On this table here, I will try to come up with, actually, let's do it like this. Not x and not y, so that's just the inverse of x and y. And then I will take these two columns and I will end them together. 1 and 1 will give me 1. Anything with a 0 will give me 0. And this is here my right-hand side. This is my left-hand side. You can see the results here for all combinations are the same as the results here for all the different combinations. Therefore, by perfect induction, this identity is true. Now, you can do it for any Boolean expression. If, for example, in an exam, I tell you, prove this left-hand side of this really complex expression is equal to this right-hand side of, nevertheless, not less of a complex expression, but they don't seem to be related whatsoever, and you have no idea how to manipulate it. You write two truth tables, and then you show, well, these are the results for all the right-hand side, these are the results for all the left-hand side, they are identical. Now, being the meanie that I am, I might give you something with 6 different variables, which means that if you take the perfect induction way of doing things, you end up with 64 different rows, which makes you think you might want to stare at the equation a little bit more. Maybe do it by Boolean algebra. I'll see what mood I am on the day of the when I write the exam. Yeah.
With duality, will the truth tables for the dual of every function to be the same?
Sorry. So
if you take any function,
yeah.
and you take its dual, will the truth tables be identical?
It will not be identical. In fact, it will be nothing identical. It will be nowhere near identical. And this is what I said when I talked about duality. It's not a way to manipulate expressions. It's a way to prove theorems. So if I manage to prove this now, then by the principle of duality, I can then show that the other way to show Demorgans theorem is true as well. But clearly this will not give you the same truth table. Speaking of Demorgans theorem, it doesn't necessarily have to be with 2 variables. We can extend Demorgans theorem to be 3 or more variables. In fact, you can have as many variables as you wish. For example, if we had x1 or x2 or x3 or as many x's as we want, xn, and we complemented this, it'll be the very same as not x1 and not x2 and not x3 and not xn. And the duality of this is true naturally as well. x1 and x2 and xn inverted will be the same one as not x1 or not x2 or not xn. Now the Demorgans theorem comes in very, very, very useful because we always have negations of large expressions, and this will actually be very useful when you manipulate your equations, and it will help you simplify things. Please make sure you know how to sort of go from one side of the theorem to the other side. It's not actually that hard to remember, but it will come in so many times, it's worth knowing it. Just as an example, if I had this kind of expression, A or B or C or D all inverted, it will be the same as saying not A, not B, not C, whoops, not D, which sometimes we can manipulate this form a bit easier because now we don't have this sort of thing in parenthesis. Because as I said, you can think about this as if there's parenthesis around this whole expression, where here we're sort of separating the different variables. And therefore we can start manipulating them with other parts of the expression. So someone, where is he? Someone said he knew how De Morgan looks like. This is how De Morgan looks like. And we said he was sort of a friend of George Boole. And he's the one that came up with the Demorgans Theorem. He was actually slightly younger than George Boole. He was born in 1806, which is, what, 9 years before George Boole. Nevertheless, they were friends. In fact, he was English, but he was born in India because his dad used to work for the military, and his dad was set in India, but they moved back to England after this guy was born. Now, I can't tell you a story. It's interesting. I went and researched the story. Give me some credit. So what's his story? So he went back to England when he was a baby. Well, his family went back to England. It would be a shame if he went by himself. When he was 16, fairly young, he attended Trinity College, where he got a Bachelor of Arts. He was going to get a Master's of Arts as well, but back in the days when if you wanted a master's degree from Trinity College, you had to go through some religious test, and he opposed going through religious tests, so he just dropped out. But then he became a lecturer for mathematics in London University, which later became University College as part of the University of London. London University and University of London, not quite the same thing. But apparently he was quite a good lecturer. He used to really like to challenge his students. He used to come to lectures and teach about stuff, and then at the very end give them some really challenging questions and tell them, okay, now you go home and you think about this, and show me your results the next time. Which is not a bad idea. What do you say? Yeah? He actually used to collect them and check them, which is something I used to do a few years ago, but then the class sizes started growing and growing and growing, and I cannot possibly mark 150 works every week. So I won't do that. So that's his story. He's the one that came up with the Demorgans Theorem, along with some other mathematical discoveries that nobody remembers, because his name is now always goes with the Demorgans Theorems. Now, let's have a bit of an example of how we simplify things. Now, when we say we want to simplify things, yeah, shh. When I say we want to simplify things, it means that obviously we want to reduce the number of variables, the number of operations that we have. Now let's define the term literal. So a literal is very similar to a variable, so A, B, C, D in our case, but it could be either the variable or a complementary form of the variable. So A is a literal, not A is also a literal. So taking this definition into account, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 literals in this expression. I want to somehow simplify this expression and make it have the smallest possible number of literals that I can. So how do I start manipulating it? Well, let me look for patterns. I see I've got an AB here, and I've got an AB here. I've got not AC here, I've got a not AC here. So these are the kind of clues you should start looking for. So let's start off with sort of grouping them together and see how we go from there. So I'll have this AB, and then I'll move this ABCD in here. And then I'll have that one from here. I'll just keep it from before. And then the one that I said it looks kind of similar to it, I'll bring it down. And that fifth one. And I did not actually change anything in the expression. I just reordered my, my terms. Is that a question? Stretch? Stretch. But now I can do things like take this AB AB, and factorize those two out together to make that AB1 or CD. And in a similar way, I can then take that not AC and factorize it out and be left with D or not D. And for now, I'll leave that last term intact. Obviously, this becomes a 1 because 1 or something is always a 1. This also becomes a 1 because something ORed with its complement is always a 1 because one of them has to be a 1. And I end up with AB or not AC or not A, B, D. Can I simplify it any further? Ideas? If you printed the note, it's right in front of you, so some of you, at least someone need to be have some clue. Yeah. Let's try and factorize this B here together. So I have B, A, or not AD, or not AC. Do you remember this? We said X or not XY would be X or Y. Similar form to this. So this can become B, A, or D, and not forget that term there. Can I simplify it even further? No? Is there any way to know that I cannot simplify it any further? I don't know, because when I was here before, I said, is there any way to simplify it any further? A lot of people just gave me blank looks. Others sort of saw in the notes that you can, but didn't say anything. Some of you thought this is the way where we stop. And then we tried this, and we got here, and now everyone says no, because the notes say no. But there's the question, is there a way to know that we got to the end and we cannot actually simplify any further? Maybe if we manipulated it to begin with in a different way, we would have ended up with something which is simpler. This, by the way, has 5 literals in it. Oops. It's 5, not 5. In comparison to the 15 that we started with. No, there isn't a way to know that this is it. There isn't a way to know, not by using algebraic manipulations, that we actually got to the simplest form possible. Because we might go one way, we end up with 5, but maybe if I reordered that first line a bit differently, I would have ended up with something with 4 literals, maybe even less. We will see next week how we do know how we get to the end. Anybody knows why this is related to what we're doing at all? Anybody knows who it is? It's what? It's not, it doesn't call Mikey, no.
Lion King.
Oh, Lion King. Yeah. But what? It is from Lion King. What's the name of the bird? Zazu. Who made the voice of Zazu? Ron Atkinson. We saw him before in the video. How is Ron Atkinson related to all of this? He's not a doctor. He's an engineer. In fact, he's an electrical engineer. from Newcastle University. He got a bachelor in electrical engineering from Newcastle University. He was gonna do his masters of engineering, of electrical engineering, in Oxford University. And then while he was studying, a friend came up to him and said, "Hey, we've got this entertainment night. Can you come and tell a few jokes?" And he did, and he was pretty good at it. And he was so good at it that he changed his career and became a comedian. That's to show you that not all is lost for you. There's still alternatives. Now you can go.